Assalamualaikum warahmatullahi wabarakatuh. Dear students, in this session I'm discussing the concept of the homoscedasticity. Very briefly, now inshallah I learn how to check for the homoscedasticity. And this is part of the lecture 10 we have already discussed. And this homoscedasticity, dear students, is related to the classical linear regression model assumptions. And among those assumptions, one assumption is homoscedasticity, right? So what is meant by homoscedasticity resonance? Simply, the technical way is just you can say the variance of the error given each value of x that is constant, right? This is just showing the variance is constant, right, for all I. So this is just the graph. Look, for each value of x we have the variance is just constant, and this is the variance of the residual term. This is just showing the residual. So if these variances across each value of x is just not constant, then the assumption of homoscedasticity is simply violated, and we say there is heteroscedasticity. Look, this is just a graph of the heteroscedasticity. Here we have the variance, but the variance across each given value of x is just not constant. Here we have small variance, here we have more variance difference. So this is the situations where we have heteroscedasticity. What's the problem of heteroscedasticity difference? The problem is, you can say, the standard error is just not true. The standard error in the situation of the heteroscedasticity is either underestimating or overestimating the variance we have. Why? Because the standard error is just giving us one simple standard average of all. So if you have more variance, right, that is just kind of underestimated, and if you have lower variance in the model, that is just overestimated. In both of the situations, if there is underestimations and overestimations, so the t value is either inflated or deflated. Okay, dear students, simply you can just see that when we are testing for the heteroscedasticity, so the conclusion is just here. You can say what problem does heteroscedasticity cause in the OLS? We can say inefficient estimates. This is what I've explained simply. It means the variance is not minimum, although the estimators they are unbiased. It means the beta 1, beta 2, they are just giving you the correct average, right? But they are not efficient, or you can say they are not minimum. And once that's not minimum, so truly you can say there is uncertainty in the standard error in that situation is invalid. And once the standard error is invalid, you can say the coefficients or the standard error of the coefficient is biased. In that situation, the t value is either inflated or deflated. Why? Because if the standard error, dear students, is higher, then you can say the t value is just deflated. The t value is just giving you simply the smaller value. Why? Because in the t statistic, if you remember, we already discussed that for in the t statistic, how the t statistic is just computed. This is equal to the coefficient. If you have the beta 1, this is the coefficient, right? And this is divided by the standard error of the beta 1, right? It's the standard error of the beta 1. So I'm just asking a question: what if the standard error is overestimated? It means the standard error is just higher than its actual. Then you can say the t value in that situation is just small. Why? Because the numerator, when it's just divided by the higher denominator, the t value is just small. But if the standard error is just underestimated, you can say the t value is just inflated. In both of the situation, the p value is just not given true, because the critical region, dear students, if you have the normal distribution curve like this, dear students, right? If the t value is just underestimated or overestimated, in case the t value is just underestimated, so you can say, sorry, if the standard error is just underestimated, the t value is just simply higher, you can say, all right? And when it is just higher, you can say you're just going in this extreme into the right. In this situation, there is more chances of the type 1 error, right? It means it's less likely to reject it is more likely to reject the null hypothesis when it's actually true. And if the standard error, dear students, this is overestimated, right? So you can say the beta 1 value, that is just small, and if it is just small, then it is just getting closer to the average value and there is just chances of the type 2 errors when you fail to reject the null hypothesis when it's actually false. So this is the error reassurance of the invalid standard error. So you can say the wrong p-value once the t-value is just not okay, either inflated or deflated. So you can see the critical region value is also just different. That's not reliable. Similarly, reassurance the incorrect confidence interval. This is really important. The confidence interval is just the lower limit and the upper limit, and that is just based on the standard error. And once the standard error is just not reliable, then you can say the confidence interval is also not true. And poor model diagnostic reassurance, the model is also misspecified, right? By the misspecifications mean the model may be just missing some very much important value, a variable in the model, and because of that the heteroscedasticity exists reassurance. So the conclusion is simply you can say reassurance the model should be homoscedastic, there should be homoscedasticity, and if there is heteroscedasticity in the model, then we should check the heteroscedasticity, and then there is a special way of running regression, inshallah I will learn we have for that, and that is the robust regression. Okay, now you are learning in this data that how you can find out or you can just detect the heteroscedasticity. Okay, for testing heteroscedasticity reassurance, we are using the Stera software. Just click on the file, and I'm importing the file because it is my data is in Excel file. Just click on the browse, and here I have a special file by the name of heteroscedasticity, right? This is okay. Now just click on the import file. First row as a variable name and click OK. Okay, this is in this datasets we have GDP. These are dependent variable, and government spending, exports, and investments. They are independent variable. I'm just interested to know how these independent variables they are affecting GDP or gross domestic product, right? So for this purpose, before I'm just making sure to run regression, then you should check for the heteroscedasticity, whether the output based on the OLS is just reliable or not. Okay, so in Stata, you should just type reg or regress, and then what is your dependent variable, you should just put it first, and all of your independent variable just click on them. So we have here the GDP, these are dependent variable, the government spending, this is one independent variable, exports is another, and investment, this is the third independent variable. Just press enter the reassurance. This is the output, but here we have not yet checked for the issue of heteroscedasticity. Now what is the output? The F value reassurance is less than 0.05, so you can say the model is overall significant, right? And our three independent variable, we have the government spending, this is insignificant. You can say there is just insignificant relationship of government spending with the GDP, and two variables, exports and investment, they are significant, right? So you can say the interpretation is just simple. You can say a unit increase in the export is just leading to $0.931 increase, you can say, in GDP, kind of affecting GDP in this way. So this is just dear students the p value. So we have two variables, they are significant, as one is not significant. Why? Because the p value is just higher than 0.05. But keep in mind, this output is only reliable, right, and consider for your research analysis if there is no heteroscedasticity. And for this purpose, we are just having a test of the heteroscedasticity, and that is the Bruce-Pagan test, right? The test is just named by the Bruce-Pagan. And just type head test and press enter. And the Bruce-Pagan test, we have the p-value that is 0.02. But before interpreting this value, just look into the null hypothesis. The null hypothesis is just stating the constant variance, means we have we have the constant variance, dear students, simply, right? But our claim is we say no, the variance is not constant. For example, if the variance is not constant, that is the situation of heteroscedasticity. So if the p-value is less than 0.05, it means we are rejecting the null hypothesis, which is the constant variance. And just we are stating that the model is having the issue of heteroscedasticity. Once again here, If the p-value response is just greater than 0.05, then we can say there is no heteroscedasticity. But in these situations, we are just observing we have the heteroscedasticity response. Okay, so in your research analysis, this p-value, the variable p-value, is that it should be just greater than 0.05, unlike the statistic we have here. Okay, why? Because the constant variance is just our null hypothesis, so we do not want the heteroscedasticity. That's why this value should be greater than the p-value 0.05. Hopefully this is just clear. So this is the situations where we have the issue of heteroscedasticity, right? Okay, now I'm just giving an example where we do not have heteroscedasticity, and for that example, I have just one more file. Just click on the file and click import, and in the Excel spreadsheet, I have one more file, and that there is we have homoscedasticity. Okay, the same file, but well, with a little bit variations in the data. Okay, this is another file, right? Now once again I'm just checking here the effect of the three independent variables. So just you should type regress or reg and add dependent variable. This is GDP, right? And these three are independent variable. Simply press enter. So this is the output response. But in these situations, we have all of these three independent variables. They are just significant, right? And the if value is also significant, so the mark is significant what. But now, before considering this output, we are just checking for the heteroscedasticity. So you are just using the head test, and this is the test of the Bruch-Pagan response. Okay, so again here the the p-value now here is just greater than 0.82. It means we cannot reject the null hypothesis. We are failing to reject the null hypothesis. This means the data is just homoscedastic. Once again, I'm just repeating, if the p-value is just greater than 0.05, then the data is homoscedastic, or you can say there is no heteroscedasticity, or the problem, the issue of heteroscedasticity. Now, dear students, you are learning that what if we have heteroscedasticity? What is the problem? Very much simply, right? In our previous example, once again, I'm just importing back my previous file, right? Where we have the heteroscedasticity. So this is a file where I have heteroscedasticity, right? Okay. Yes. Okay, I'm just once again running the regression. So type reg, right? And we have GDP. This is our dependent variable, and these are our independent variables. So now this is the output, and when you just check the heteroscedasticity, so you can say yes, we have the heteroscedasticity results. In this situation, have to remove the heteroscedasticity. We are just running the robust regression, and that is just standardizing the error. In that situation, the OLS is then appropriate, and we can say the output is just acceptable, right? Okay, just the solution of the heteroscedasticity, you should run again the same regression, just regression, and take the dependent variable and all independent variable, and after just put the comma, and you should type robust, right? And when you just press enter, this is just the output which is just acceptable. Why? Because the standard error is just standardized, the variance is not standard, and you can say the issue of the heteroscedasticity is just solved. Then now you can use this output for your analysis, right, or for your research. So you can say the if statistics still is or are significant, and we have now two of our independent variables, they are significant. Okay, this is the output response. Now this is reliable and acceptable, and you can use it. Why? Because we have just run the robust regression where the issue of the heteroscedasticity is just removed, dear students. Okay. One more method, dear students, if you just try to know have to visualize if there is heteroscedasticity or homoscedasticity, right? So we have one more method, and in that method just you are predicting the residual, right? And we have the command just predict residual. So the residual is the u hat. This is residual, or the error term, if you remember, and the function is just you should type residual. Here I'm just in Stater, this is a command for just generating the residual. And how you can generate the residual, you know, from the y, actually we are just subtracting from the, sorry, from the y predicted, we are just subtracting from the y hat, we are just subtracting the y actual, and this is just giving you the residual, right? So we have just created the column for the residual. Just click here and you can just observe it here. This is the column, the u hat means this is the y predictor minus y hat, right? And once you just find out this column, when you have this column, dear students, the second step is just predict the fitted value, or you can say the prediction, right? So that is just type predict, and we need y hat now, and just after the comma you should type xb, right? Now we have one more column here, students, and this is the y hat. So this is u hat, this is the residual, and the function is just simple, and that is the y hat minus y actual, and this is the y hat. This is just determined and predicted based on the regression. If you have the coefficients and the beta value, then you can just predict it, right? So the stata is just predicting the y hat through command directly. Okay, now the last step, dear students, we are just using the scatter plot, the visualization. Just type the scatter and the u hat, this u hat. I'm just trying to check the u hat against the y hat, right? U hat, this is just the y-axis, and the y hat, this is I just need in the x-axis. So look, dear students, now this is the graph. Okay, in this graph, if across all given value of x we have, if these values are constant, then we say there is homoscedasticity. So somehow the graph is really difficult to observe whether it's constant, but you can say the values across each, the values of the error term we have across each value of x is just not looking constant. In those situations, you can say somehow the heteroscedasticity is just observed in this graph. Okay. These are just the value, these are just the predicted values, and this is the value of the residual, and we are just checking whether for each given value predicted, what is the variation on the dispersion, or you can say the fluctuation of the residual term around. If there is just no pattern, or you can say if there is just no variations, and that is just looking same across all these values, then you can say there is no heteroscedasticity. But some have in the graph, it's really difficult, but you can just see that the values, they are just different. You can say some values, they are more cluster here, you can say more cluster, but they are just dispersed in this area. So from here you can just observe there is no homoscedasticity, or you can say there is heteroscedasticity, right? Hopefully the idea of the checking the homoscedasticity, or you can say heteroscedasticity, is just clear. Assalamu alaikum wa rahmatullahi wa barakatuh.